That's good. Now is the audio bouncing? Yeah? All right. I will begin. Heavenly Father, we thank you for this day. Thank you for these students. Just pray that you'd just help us to have a productive day, that we'd glorify you, Lord, and we do. In your name I pray, Lord Jesus. Amen. If you watched the help session from yesterday, I worked a bunch of problems in Chapter 12 in there, and I tried to actually discuss the tail end of Lecture 22. But then I forgot to pan the camera up. But I'll just let you read it. There's no point in me going over it again. Basically, I just proved the characteristic theorem and the fact that we have a cancellation property in an integral domain, right? That's important. In an integral domain, a commutative ring with unity, if you have AB is equal to AC for A non-zero, it follows that B has to be equal to C. Even though A inverse need not exist, we have that. So this is Lecture 23. Which is on ideals and factor rings. So let me start with a definition. So definition, a subring A of a ring R is called an ideal if for every A in A and R in R, both AR and RA are elements of A again. So I think Dr. Sprano calls this uber closure. So you have multiplication of things not only in, of course, if it's a subring, it means that it's closed under multiplication of things in the subring, right? But this is more. We're saying also that if you take elements possibly outside the subring and you multiply it by things in A, you're again back in A, whether you multiply on the left or right. So it's more than closure. It's like, as Dr. Sprano says, uber closure. Although I would caution against using that terminology outside the context of those who understand Dr. Sprano, as people might not know what you're talking about. But anyway, theorem. If we have A is a non-empty subset of a ring R, then A is an ideal if you have the following two conditions. One, A and B in A implies that A minus B is an A. And two, if A is an A and if R is an R, then AR and RA are in A. You're like, isn't this theorem just the definition? If you're looking at this theorem kind of casually, you might not notice the distinction between this theorem and the definition. There's not much difference. What's the difference? Excuse me. What's the definition lead off? Suppose a subring A, right? So the real content of this theorem is that conditions 1 and 2 suffice to prove a non-empty set is a subring, which is also an ideal. The fact that these tests prove that A is a subring is pretty easy to see, right? Because if you look at condition 1, it gives you that A is closed under subtraction. Condition 2 gives you uber closure. But in particular, it gives you closure under A, right? Because if R is an element of A, it's also an element of R, right? So we get that basically A times B for any B in A is again an A. So we have closure under multiplication and we have closure under subtraction. Going back to the subring test, it's a subring. Once you know it's a subring, we're assuming uber closure here, so it's an ideal, right? So some applications of this. Oh, I guess I should mention, comment, 0 and R are ideals of R, right? However, R is not a proper ideal. What's a proper ideal? It's just an ideal which is not the whole stupid thing, right? 0 is a proper ideal, but it's also a trivial ideal. All right. Now, anyway, it's easy to confirm that these are, of course, ideals because if you sort through conditions 1 and 2, you can easily see that they check, right? Let's see here. A more interesting example. Let's say example 2. I'll call it example 1. Example 1, if we look at the ring of the integers, right, and if I look at A equals to nz for some fixed n in the natural numbers, mostly interested in 2 or 3 or 4 and so forth. I mean, we know what happens if you put n equals 1 there, right? Then we're just back to the integers or an ideal of the integers, which is not proper. Okay, so so here, what does it mean to have something in A? So let's pick, let's say A and B. Well, I guess yeah, A and B in NZ. What's that mean? A is equal to NA prime, and B is equal to NB prime for A prime and B prime and Z, right? That's what it means to take points in the n multiples of Z, right? And you can check, first of all, condition 1 is easy, right? If I take A minus B, I've got what? I've got NA prime minus NB prime. Factor out the n, what do you got? We can factor out n because this is a ring, right? We have distributivity. You're like, it's the integers. I know how to calculate with integers before this course. You can't take credit for that. Fine, you got me. You got me. You knew integers before you came here. I don't deny it. I believe in my heart you knew what integers were before you darkened the doorstep of liberty, probably. Let's see here. So this is an element of NZ anyway, is the point. So we've verified condition 1 for arbitrary points in the alleged ideal. And then if we let R be a integer, any old integer, right? Then if you consider 2, we should look at, you know, A times R. By the way, that's equal to R times A. So let's just, in the commutative case, right? If you're dealing with a commutative ring, you don't have to check for both AR and RA, right? Because they're equal. So it suffices to check for one. Anyway, so this is R. What was A? A was NA prime. So you can rewrite that. That's N times RA prime, which is, by the way, an element of NZ. So there you go. So multiples, positive integer multiple of the integers forms an ideal. And the integers, in fact, this is sort of like the quintessential ideal. Well, it's not entirely true. It's actually a very good example of what's called a principal ideal. Let me show you what that is. Now, this is something that I'm, I really like Galilean, but I really do think this should have a standalone definition and not be buried in an example, so I'm giving you a definition. Let R. Tired of that marker. Try again here. Oh, man. Come on. Eventually I'll find one I like here. Okay, so this is the definition of a principal ideal. So here we have R, a commutative, ooh, this is a weird one. Commutative ring with unity. Ooh, this one's stinky. commutative ring with unity, and suppose A is an element of that ring, then we define the quote-unquote principal ideal generated by A as follows. It's angle bracket A, close angle bracket, equal to AR such that R is in the ring. So this is the definition of a principal ideal. Now, so for example, oh, goodness gracious, so sorry. So, comment. In example 1, right, we showed, what did we do? We showed that the ideal generated by n, which is what? N R, such that R is an integer, right? I mean, that is exactly nz, right? We just proved that that is an ideal. Okay? Now, that doesn't prove that this is an ideal, does it? I mean, we could also write that this is equal to A times R. That's another nice notation for it. And since we're assuming commutativity, for what it's worth, it's also true that this is R times A. All right. Okay, so, that example doesn't prove that that's a legitimate use of the terminology ideal, right? So we should make a little theorem. Theorem, the principal ideal generated by A is an ideal. And I'm assuming all the rights and privileges that are given in the definition. Eventually I'm going to find a blue marker I like here. So here's the proof. First of all, notice that A times 0 is equal to 0 is an element of the principal ideal generated by A, so therefore it's non-empty. So it's a non-empty subset. I'm going to use the ideal test over here. So let's say x and y be elements of the principal ideal generated by A. Then what's that mean? There exists x prime and y prime in the ring, such that what? I think all my blue markers are dead. Yeah, x equals to, oh, one works. Check it out, ax prime and y is equal to ay prime. That's by the definition of what? Sorry, it gives me joy. So that's by the definition of principal ideal. And then you take the difference, right? What's x minus y? Well, that's ax prime minus ay prime, which is, by the way, a times x prime minus y prime. Now, x prime minus y prime is the subtraction of two elements in a ring. Therefore, it's in the ring. Consequently, we have a times something in the ring, which, since a is an ideal, since I'm an idiot. This is what? This is a times something in the ring. Therefore, this is an element by definition of this set, right? Okay. So that gives us 1 in the ideal test theorem, right? And then 2, if you look at x times r, right? So a little caveat here, let r be an element of the ring. All right, one of my pet peeves with you guys is you never tell me where stuff is coming from, which is, well, not all of you and not all the time, but you know what I mean. All right, ax prime r. What is that? Well, that's a times a product of two things in the ring, x prime and r. So it's again in the principal ideal generated by A, by definition, right? Thus, this is an ideal by the theorem I stated at the start of today. I mean, if you look at it, you see why this is the quintessential principal ideal? The reason that an arbitrary principal ideal is a principal ideal. Did you move back? Or were you over there before? Were you over there before? Oh, man. So if I could talk backwards, we did over here. It's okay. Nicole is trying to teach me not to use her on the camera. It's like some of you, when you get married, will mess up doing the dishes when you first are asked to do it so badly that you might not be asked again. Of course, I would never do anything like that. Not on purpose, anyway. I'm just bad at that kind of stuff. In ways I never anticipate. Let's see here. Where was I? Yeah. Okay, we don't need this anymore. Moving along. So there's tons, just tons and tons of great applications of this. I'll just list a couple here. Example 2, you could look at the ring of polynomials with real coefficients. Then the ideal x is what? That's basically, if you look at that, that's what? That's like x times f of x, such that f of x is a real polynomial, right? So can you guys describe for me what that would be in words as opposed to just the symbols I used right there? What's that? X in the reals? No. These are polynomials. G of x such that what? G of 0 is equal to 0. Or you could say they're the polynomials with no constant terms, or 0 constant terms, right? Another definition, you can generalize what we just did to more things. So if you have a1, a2, an in the ring, then you can define bracket a1, a2, an as basically linear combinations with these as coefficients and then arbitrary ring elements. So like a1r1 plus a2r2 plus anrn, such that what? Well, such that r1, r2, rn are elements of the ring. So this is the ideal generated by a1, a2, an. Incidentally, this is not a principal ideal unless it happens to be the case that n equals 1. All right, principal ideals generated by just one thing. This is not necessarily one thing. I mean, you could do something stupid, right? Like the silly example. I guess this could be a principal ideal if you did something like this, right? Like x and then 2x, right? This would still be a principal ideal, right? Because if you think about it, you can just collapse this. It's just the same as that, right? So unless there's some kind of like interdependence of these generating elements, it's generally the case that that's not a principal ideal. However, there's a theorem is an ideal. All right. That is one of your homework problems. All right. I think I'm going to use the projector for what follows because there's a lot of writing and it's not that surprising what I'm about to write. So, That'd be tricky. I didn't bring my laptop. All right, so sorry about that. So you might wonder, what's the deal with these ideals? Like, why are we looking at ideals? What's the point of looking at an ideal? The point is just this. What is it? Oh. Okay. The point of it is that an ideal allows us to construct a quotient ring, or you might call it a factor ring, in the natural way. So here's the theorem. If we look at let A be a subring, all right, let A be a subring of a ring R, then, R mod A would mean the left cosets, well, additive cosets, let's say, okay? So this is R plus A, such that R is an element of R, right? So this we've already talked about. I mean, R is an abelian group under addition. This makes sense, right? We can look at the set of cosets. All right? And now here's the theorem. That's just a setup. I'm not quite done with the setup yet. And we define, and I'd say possible operations in the following sense. So like R plus A plus S plus A equals to R plus S plus A, and also R plus A times S plus A is equal to RS plus A. For each R plus A and S plus A in the set of cosets, we define these possible operations. I say possible operations because in the case, well, let me just finish this. Then R mod A forms a ring if and only if A is an ideal. Okay. So I'll just show you part of the proof today, all right? I'll say some of it in words. I won't write too much. First of all, the additive part, right? Let's look at this. Let's suppose A is an ideal, right? Well, then it's a subring, right? Which means that it's an additive subgroup of R under addition, right? So then A is normal subgroup. Sorry, I said it wasn't right. Not very good. Keeping my word on that. It's a normal subgroup of R under addition, right? So with respect to addition, the factor group is already defined. We did this before. We already know what it is. So the addition is well defined. We don't have any work to do there because we already did that work before. Multiplication, though, well, that's different, right? So for multiplication, suppose that we have S and S prime and T prime in the ring with S plus A equal to S prime plus A and T plus A equal to T prime plus A. What I'm saying is, suppose you have two different representatives, all right, of a pair of cosets, S and S prime or T and T prime. Notice that we have that S prime minus S is equal to A for some A, and we also have that T prime minus T is equal to B, where B is also some element of A, by definition of coset equality. Well, not by definition, but by the thing you guys didn't prove on the test because I had a typo. Lucky for you. Yes? Yeah, I think many of you would have got that, actually. I think that my typo was destructive in that case, more than usual. But helpful for some of you who only half understood and still got credit. So we'll leave it at that. Like, please make more typos. No, let's not hope for that. Anyway, so the point is, s minus s prime is a, t minus t prime is b. Both of these things are in a. What's that mean? That means you can solve this. We have equations like s prime is equal to s plus a, right? T prime is equal to t plus b. So if we calculate s prime t prime, we get what? We get s plus a times t plus b, which is, by the way, st plus at plus sb plus ab. This is something in like AR. This is something that is in RB, right? And well, this is just in A again. So this AR is how can I say this? Anyway, this getting to the point. This is an A again, and this is also an A again. Why? Because here I'm looking at the product of something in A and something in the ring. So it's again in the ideal. And here we're looking at a right multiple of something in the ring by something in the ideal. Again, it's in the ideal by Uber closure. So in A, sum of three things in A, again in A. So therefore, s prime t prime minus st is an element of A. So what does that show? Therefore, st plus A is equal to s prime t prime plus A. Which shows you, of course, that the multiplication is well defined. So what's left for us to show then? We should show distributivity property and the associativity property of the coset multiplication, right? I've typed those out in the notes to let you look at them. I'll just say it in words here. It's nothing more than the definition of the multiplication on the cosets paired with the respective associativity of the multiplication on the ring or the distributivity of the multiplication on the ring. It's very, very straightforward. So there you go. That's why we want to look at, you can see right here why we need both left and right ideals, right? Because we need, in order for this multiplication to be well defined, we need to be able to absorb things on the left and the right to make this make sense. That's the if and only if also, I have the other direction in the notes. I'll let you read it. I don't think it's worth class time to go over, but it is true. You do need that it's an ideal. If you try to do this for a subring, you can easily produce from the thing that's not that's disrespecting Uber closure. You can prove that the multiplication is not well defined because of it. It's not that hard. All right, but we should go on. All right, so where was I? So you have some great examples in here. Let's see here. Where was I? Example 4. If you look at, this is his example 12. His example 10 and 11 I'll probably talk about in the type notes. But example 12, he has the ring of polynomials, Rx, and he looks at the principal ideal generated by x squared plus 1. All right. Well, first of all, that is a principal ideal, so it's an ideal. So we can look at the factor ring or the quotient ring formed by taking real polynomials mod this ideal. Right? So we can study that. You know, we can look at R of x mod x squared plus 1 in this case. And what would that be? That'll be things of the form g of x plus this ideal, such that g of x is what? Yeah, just an arbitrary polynomial with real coefficients, right? So what's that look like? How does it work? How do we calculate in this sort of thing? Let's see here. Let's try to understand what would it mean for if we had, g of x plus x squared plus 1 equal to h of x plus x squared plus 1. What would that mean? What does that mean? It means g of x minus h of x is an element of the principal ideal generated by x squared plus 1, right? So what that means is that g of x minus h of x is equal to x squared plus 1, right? Times some other polynomial, whatever you want to call it, j of x. I guess, that's true. I'm not sure how much insight that gives us. Let me look at something a little bit more specific. So let's see here. Could you simplify, let's say, x squared, plus 2x plus 2 plus x squared plus 1. What would this look like? So this one you could do what? You group together, you've got this x squared plus 1, right? So this would be the same as just 2x plus 1 plus x squared plus 1. Do you guys see that? So what I did was x squared plus 1 can get absorbed into here. We go back to properties of cosets, right? So if you have h, it's equal to h, or in the additive notation, which is where we are, h plus h is equal to h again, right? So if, x squared plus 1 is inside the subgroup, right? In this case, a subring. So anyway, there it is. Let's see here. How about this? What if we had x squared plus x squared plus 1 equal to minus 1? Is this true, is my question. Why is this true? It's because, right? Because this is equal to minus, there's different ways to look at it. Here's one way. If I add x squared plus 1 to this side, what do I get? I can do that without changing it. Why? Because I've just added something inside here again, right? You have to go back to the properties of cosets that we did before. And anyway, so that's x squared, right? So what can we say here? Basically, we have, it appears that x squared is equal to minus 1 mod x squared plus 1. Or another way to look at this is in this quotient ring, x is behaving like the imaginary unit. So if you really think about this right here means that I can take f of x, let me be a little bit more explicit here. I can take the polynomial a naught plus a1x plus a2x squared plus a3x cubed plus dot 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 dot, right? Let's say plus akx to the k plus this x squared plus 1. And what can I say that's equal to? I can say that's equal to what? A naught plus a1x, right? Minus a2. See, I can trade this x squared. X squared is basically congruent to minus 1 mod x squared plus 1. And x cubed is what? It's really just minus x, right? So this gives me minus a3x and so forth. So if you recollect this, you see what you really got is just like b naught plus b1x plus this for the appropriate, collapsing of the a's down into the b naught and a1. So an arbitrary thing in this quotient by x squared plus 1 just looks like, b naught plus b1x. And if you want to multiply them, you can use the rule x squared equals to minus 1 to guide how you simplify the representatives. The more I talk about this, the more it should become clear to you that this is just the complex numbers in disguise. Yep.
I'm curious for that first one, you're writing down the x squared plus 2 plus the x squared plus 1.
Mm-hmm.
If you factor that to be, oh, never mind, I'm sorry. I didn't figure it out.
Okay.
Yeah.
That's cool. Glad to help. Let's see here. So anyway, it's a great example. Brings us to our next pair of definitions. Excuse me. I'm proud of myself. I have a very, very strong temptation to spend 40 minutes of class time going through this with painstaking care. But after we do that, what does it gain us? Not that much, unfortunately. Yeah.
Does this example that we just did show that we can create like basically an isomorphism from polynomials to complex?
We are getting there. Eventually, we want to discover how to use polynomials to create things like complex numbers. I mean, that's pretty much what that is. But we're going to understand that example more deeply as we go on in here. So definition. Prime ideal. What's a prime ideal? A prime ideal, here it is, of a commutative ring with unity. Commutative. Oh, wait a minute. No. I'm sorry. Excuse me. Commutative ring. I don't see any unity here. I'm overstepping my bounds. Just commutative ring. Commutative ring. Prime ideal of a commutative ring is a proper ideal. Come on. Is a proper ideal A of R such that, finally, here's the punchline. A and B elements of A, all right, imply what? Either, not either, I should just say A is an element of A, or B is an element of A. I mean, they could both be an A, of course, all right? That's a prime ideal. If you can look at something, a product of two things, and that product of two things is in the ideal, the prime ideal, it follows that at least one of them is in the ideal. Yeah.
You mean like A has to be element of A for the first one?
Is that what I said? Oh, man. Yes. Thank you. Was that also your question? Yeah. Yeah, that's a very unfortunate typo. Thank you. Goodness gracious. Yeah, that was not good. A maximal ideal is kind of what it sounds like. Maximal ideal A of R is an ideal of R proper. Sorry, I got to assume proper ideal. Proper ideal of R such that when B is an ideal of R and A is a subset of B is a subset of R, then what? I guess I probably should cross out this when and put an if. Trade that when for an if. If then what? You either have A equals to B, right? Or what? Or yeah, or B equals R. Or you could say B equals A, and I mean, if you, okay, fine. For the sake of syntactical symmetry, B is equal to A. There you go. Here's an example. Where was I? What example am I on? Lost track. Example 5, I suppose. If we look at Z36, in there you have 2 and you have 3, right? These are subrings. 2, for example, is like 0, 2, 4, 6, 8, so forth and so on. 3 is what it sounds like, 0, 3, 6, 9, da 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 da. And then what's below this? You got 6 down here, right? What else is below the 6? I mean, the 2 is the 4, right? And below 3, there's 9. And then what else? Like, what's 18? Where does that go? Here? And what's that? Well, not directly. What did you say? You said 12? Where's 12? 12 is here. Where's that come? That's from this, right? And also from that. And then I guess down here is 0. So what I'm drawing here, I didn't need to draw all of that, but it's fun too. This is the subring lattice of Z36, right? And so there's all the ideals, proper and otherwise, of Z36. So there are 2 things here that are maximal ideals. What are they? Right. These are maximal ideals because, well, sort of like the whiz. You know, nobody beats them. Let's see here. So we have 2 major theorems about principal and maximal ideals, guys. Let me state those for you. Theorem. Let R be commutative ring. All right, with unity. And let A be an ideal. All right, of R. Then R mod A is an integral domain all right, if and only if A is prime. That's the first theorem. The second theorem, which is important, is that if we have R a commutative ring with unity, All right. And A, an ideal of R, then what? Then R mod A is a field, all right, if and only if A is maximal. Example 15 in this section, all right? He goes through a really beautiful calculation to prove that the ideal, the principal ideal generated by x squared plus 1, all right, over the real polynomials, the one I have just erased there, he proves that that's a maximal ideal, which isn't surprising to us because we had the suspicion that the quotient of real polynomials by x squared plus 1 was the complex numbers, right? We know the complex numbers are a field, so that's, it's comforting. But to actually show that that x squared plus 1 ideal is maximal is a little touchy. You should study that example. I might have time to go over it next time. We'll see. But, excuse me. The proof of both of these theorems, not that complicated, but of course they require a little bit of time. Let's see here. So let's pick on this one. So proof. So let us suppose R mod A is integral domain. Right? We want to show that A is prime. So what should we do? Let AB be an element of A, right? That's the thing that we get information about. We're trying to prove that if AB is an element of A, first of all, A is an integral domain, right? So that already gives us that it's a proper ideal, right? So we're trying to show then that either A is an element of A or B is an element of A. Okay? So what's this then what? Well, AB plus A is equal to 0 plus A, right? It's an ideal. The factor ring makes sense. So this implies what? This implies that A plus A times B plus A is equal to A, right? I mean, the point is that this is the 0 of the factor ring, right? We have a product of two things being 0. It's an integral domain, we're assuming. So therefore, either A plus A is equal to A, or B plus A is equal to A, right? I don't need the either. I should just say thus. It's not an either or. It's could be both, right? And hence what? A is an element of A, or B is an element of A. Therefore, A is prime. So that's which direction? That's, we just did, this is if and only if. We have just done the forward direction of the proof. Let me try to do the reverse direction. So we should do what? Assume A is prime. Right? And then we have to prove that R mod A is an integral domain. So let x plus A times y plus A, right, be equal to A. I'm assuming that the product of two things in the factor group, the quotient group, is 0. To show that it's an integral domain, we have to show that one or the other of those is 0. all we have to work with is that a is prime. But this is what? This tells you that xy plus a is equal to a. So therefore xy is an element of a. Hence, what? X is an element of a, or y is an element of a because a is prime, which goes to show x plus a or y plus a is a, which is to say it's 0. In other words, there are no 0 divisors. I think these theorems are easier to prove than they are to remember. That's my experience anyway, because like a couple weeks from now I'll be like, what do we need for it to be a field? I can't remember. But anyway, next time we'll prove the other one. Anyway, thanks guys. Tonight I hope you have the rest of these typed up and send you your next batch of